Okay, greetings. This is the last class of this module. We will talk about the attosecond time delay in photoionization, which in some sense different from that in collisions, but in some sense it is the same. So, this is our incoming incident wave e to the I what is it, kz, right, or kr, k dot r. So, cosine theta I think is mu over here, and rho is kr, all right. And it is written in terms of the Legendre polynomials, all the partial waves L going from 0 through infinity. I can write it in any other basis. So, here the radial part is given in terms of the Bessel functions j, but we can write it in terms of the spherical waves e to the ikr and e to the minus ikr. So, any basis set as long as it is linearly independent works. So, in this basis set I have this I to the power L, which is actually a phase. I to the power L, I is square root of minus 1 to the power L. So, this is actually a phase L pi by 2. So, this L pi by 2 is brought out over here. I multiplied everything by I to the power L, both the terms. And then I also take advantage that the Legendre polynomials multiplied by minus 1 to the power L gives you the Legendre polynomial for an argument whose sign is reversed. So, we are going to use these properties, and in the asymptotic region we take the form of the Bessel function, which is appropriate to r tending to infinity. For L equal to 0, we know that the solution is sin kr, which is very easy to get. For V equal to 0, for 0 potential, which is for vacuum, the problem is very easy to solve. The problems are there because of the potential, and the potential has got two parts. One is the physical part, which is the interaction between the electron and the nucleus or whatever, and the second is because you are projecting the 3-dimensional problem on a 1-dimensional this thing. So, having separated out the angular part, you are looking only at the radial part, and that involves the artifact of that projection, which is why it is a centrifugal term. So, L into L plus 1 by r square. So, with every next partial wave L, the phase kr drops by pi by 2. So, kr minus L pi by 2 is coming from there, and then when you switch on the potential, if the potential is there, then there is an additional phase shift which is due to the target. So, all this information about the target is sitting in the scattering phase shift delta L. So, this is your solution, except that it is only formal. The coefficients CL are to be chosen appropriately, so that this will match with the solution that you get from the phenomenological solution, as I call it this morning. So, you have this solution, which is the solution to the differential equation, and the solution to the scattered part is the complete solution, which is superscripted by SE, which stands for Schrodinger equation, minus the incident part, because the sum of these two gives you the total solution. So, this is the scattered part, and this scattered part must correspond to the phenomenological scattered part, which is a spherically outgoing wave because it is there is an implicit minus I E t by h cross, which tells us that these are spherical waves which are coming out of the center and moving out, and this correspondence must be there. This scattered solution which is given by this difference, and this difference I have now written explicitly here. This is coming from the Schrodinger equation, the right hand side, and the left hand side is what we get or what we know describes the phenomenon. So, these two must be equal, and that will happen if C is appropriately chosen, and CL, the coefficient CL must be chosen such that the two parts on the right hand side and left hand side must be equal. The left hand side has only e to the ikr. So, everything which has got e to the minus ikr on the right hand side must go to 0 by an appropriate choice of the coefficient CL, and it is this which makes the right hand side go to all the e to the minus ikr terms go to 0. And what also pops out of it is that the corresponding coefficients, by comparing the coefficients of the linearly independent basis functions, you get the Faxen-Holzmark equation for the angle dependent scattering amplitude. These boundary conditions that we have chosen are called as outgoing wave boundary conditions, and if you express the scattering phenomenon in the angular basis in the basis of angular momentum states, then you get the scattering operator has this description. It comes out as e to the 2I delta L or I times 2 delta L. So, the phase shift is twice delta L. We have discussed this in an earlier class also. So, this is your complete solution now. This is the incident plane wave and this is the outgoing spherical wave. I have placed a superscript plus to remind us that this is the result of the outgoing wave boundary condition. Okay. Now, along with time dependence, I now insert e to the minus I omega t. So, you see that the first term is a plane wave which is moving from left to right. This e to the ikr when multiplied by the time dependent factor becomes kr minus omega t. So, it is a spherically outgoing wave, and we have the appropriate description of the scattering phenomenon in terms of an incoming plane which is moving from left to right. So, that is what defines your z axis. And now we move on to the ingoing wave boundary conditions. So, the previous ones were the outgoing wave boundary conditions. The ingoing wave boundary conditions correspond to the time reversal process, and there is a complex conjugation. So, if it was e to the plus I delta L that we chose, we will now choose e to the minus I delta L. So, this has come from our motivation to apply the time reversal symmetry and appropriate complex conjugation that we discussed in the previous class. Now, if you use e to the minus I delta L, what do we get? First, I carry this information, put a subscript here which is a superscript minus to remind us that we are now using ingoing wave boundary conditions. And if you put the coefficient CL equal to e to the minus delta L, then you get a solution which looks somewhat similar, but it is not in the details, and what you get is this. So, there are various things which are different. For example, you notice that there is a PL of minus cosine theta instead of PL of cosine theta and so on. So, these are the details which come because of this CL being chosen as e to the minus delta L. Let us write this expression along with the time dependence. So, I have now put e to the minus I omega t. So, I have e to the I k dot r minus omega t for here, and over here I have e to the minus I k r, and the minus sign is common. So, this is k r plus omega t. So, k r plus omega t now we know is spherically going inward, okay, because the constant phase will require k r plus omega t to be constant. So, k dr plus omega dt will be 0 and dr by dt will be negative, which means that r reduces as time advances. Yeah, it comes from that minus when you put that term, there is this I to the L and so on, so it comes out neatly. So, now k dot r minus omega t is a plane wave moving from left to right. If right is the direction of the z axis, if not otherwise. And what we really expect, there is this minus sign which is of importance over here. Mind you, cosine of theta plus pi is minus cosine theta. So, if you reverse this direction, this is what you really expect is this picture, not this. The one on the left has got an electron coming toward the center. What is happening in photoionization is that the electron is moving away from the center once it is born. So, the z axis is chosen with reference to what is happening with the physics that is happening over there, and the photoelectron escape direction is what fixes the z axis. So, it is not going from left to right, but right to left. Okay. So, what was your theta goes to theta plus pi, and then you have cosine of theta plus pi equal to minus of cosine theta, and the Legendre polynomial of minus cos theta becomes PL of cosine theta plus pi. So, you need to carry these terms carefully, and now with reference to this picture you have the complete description of the photoionization process as time reversed collision. So, once you apply the time reversal operator to the collision, you get spherically ingoing waves in photoionization in conformity with the fact that there is no electron which is present as a free electron before it is created as a result of photoionization, and this escapes. But if the z axis in the left figure was from left to right, the z axis in the right side figure has to be from right to left. That is the time reversal. So, everything is consistent and we can be happy, and this is the solution. Notice that it is not the same as that of the collision, it has somewhat similar form. So, one can be cheated into believing it is the same, but it is not. And because it is different, if you consider photoionization in which an electron from an initial state goes into the continuum and you use the continuum wave function. So, these continuum wave functions must be obtained according to the ingoing wave boundary conditions and not the outgoing wave boundary conditions. So, I think some of this work was earliest done by Betty and his collaborators. So, this matrix element gives you the transition probability for transition from an initial state to the final state, but the final state wave function must be obtained using ingoing wave boundary conditions. And if you do not put the wave function, the continuum wave function with the ingoing wave boundary condition, you will not get the correct angular distributions and so on. So, now there are a couple of theorems which I would have liked to do, but I am going to skip it for brevity. But I have it in this file and I am going to share this PDF with you so that you can go through it, but I will just mention what it is about. I write this solution now in a slightly different form. The cosine theta I write as the scalar product of two unit vectors n and n prime, and denoting the direction of incidence, and n prime denoting the direction of scattering, because there is nothing special about a z axis, means it is just one of those. So, I write it in a more general sense in terms of n and n prime, and then recognize the fact that any linear combination of different solutions of this type will also be a solution, which is a typical case for any differential equation. When you have solutions, their superpositions or their linear combinations will also be solutions. So, if you change these very slightly, so I am using integrals instead of summations to represent the fact that these can be changed, these directions can be changed continuously, and I am going to skip the rest of the algebra and jump to slide number 40. So, in between there are 9 slides, this is slide number 31. There are 9 slides in between in which all this substitution and manipulation of terms is carried out. But what they take us through is the optical theorem of collision theory, which you would have done, which is the statement of conservation of flux. So, one can arrive at the optical theorem using a different method also, because it is a conservation of flux. You can determine the probability current density vector, determine the flux in terms of it, and get it in the ingoing states and outgoing states, and that will give you the optical theorem. But you can also get it in a very nice manner using this method, which you might want to read about. But there is another theorem for which this approach is useful, which is called as the reciprocity theorem. And the optical theorem and the reciprocity theorem, this particular the one based on conservation of flux, I usually consult Joshein's book for that, and for this method I consult Landau and Lifshitz, but you can get both in my book. But those are the original sources, which are very beautiful and very nice sources. So, I am going to jump to, I will not discuss the optical theorem because my assumption is that you have some exposure to it from your course in collision physics. It is basically a statement of conservation of flux. Reciprocity theorem, the derivation I am skipping up to slide number 40, and I will discuss the result of the reciprocity theorem, which is coming up. This is slide number 39 and this is 40, which is where we should see it. Here, look at the very last equation at the bottom. F is the scattering amplitude, and F scattering amplitude for angles n comma n prime is exactly equal to the scattering amplitude for minus n prime minus n. That is the reciprocity theorem, and that is what is proved in these few slides which I have jumped. But the proof is basically quite simple. If you have any difficulty, feel free to email me, but I do not think there will be any difficulty. So, this is the result of the theorem. So, n and n prime, if you reverse this process, which is what you expect time reversal to do, the corresponding scattering amplitudes are exactly equal, which means that you can now very comfortably and confidently apply the photoionization, apply the time reversal symmetry to the photoionization process. It is the same for photo detachment. Photo detachment of a negative ion is a very similar thing. The electron does not exist as a free particle, but it is born when the photon is absorbed by the negative ion. So, whether you are talking about photoionization or photo detachment, the physics and the quantum mechanics is exactly the same. And we have established the complete equivalence of photoionization and quantum collisions, and we can judiciously carry over the analysis of quantum collision theory into the domain of analysis of photoionization, including the results that we obtain for the Wigner time delay and the time delay operator and the Wigner analysis and also the Smith analysis and so on. So, this is your time delay which we discussed yesterday. It is twice h cross del delta by del E. So, we are going to use this now for photoionization, with the difference that photoionization is half scattering, and therefore, we will drop the factor 2 and we will only have h cross del by del E of the phase, and this is the phase of the matrix element. So, you have got an electron in the initial state. This is the operator which induces the transition from an initial state to a final state. So, this is the matrix elements. So, we take the argument of this matrix element, taking care that the final state wave functions are obtained using ingoing wave boundary conditions, and there is no factor of 2 here. This is just h cross del by del E, and this is how the photoionization time delay can actually be calculated. You have to get these wave functions, and the work that we do in my research group, this can be calculated. The details will depend on what type of wave functions you are using. Are you using non-relativistic wave functions? Are you using relativistic wave functions? Are you using single particle approximation? Are you taking into account the configuration interactions, correlations? So, in our group we do this using the relativistic RPA, which begins with the Dirac equation and builds the correlations on that through a many body approximation, which is called as the random phase approximation. So, this is the relativistic random phase approximation. There are further corrections or variations of this method. Right now what Aarti is using is a further manipulation of the relativistic RPA, which is the RRPA with relaxation. Nonetheless, the upshot is this, that the Wigner time delay is given by the expression in the lower right box of the slide. It is h cross times, not twice h cross times, because it is only half scattering. It is h cross time the time derivative of the phase of this matrix element, and the phase is coming from the inverse tangent of the ratio of the imaginary part to the real part of the complex matrix element, which is obtained using the relativistic random phase approximation. So, this is the method. One will get somewhat different values depending on what kind of wave functions you are using. Are you using the relativistic function, non-relativistic, what type of correlations you are doing, and so on, and that is a different topic. In fact, it will be a different module altogether and not so much a part of attosecond physics only, because that is more a part of spectroscopy of estimating transitions from an initial state to the final state. So, that is a different topic, I will not get into it.
So, please explain for in the previous slide, you have the final wave function for this relativistic random phase approximation, the initial wave function, eta and kappa, like what those values denote for the wave function?
Yeah, so these are states, and physical states are represented by quantum numbers. You have to label the state, and the state is labeled by quantum numbers, and quantum numbers are those which give you information about what is measurable about the system. So, if you can measure the energy, then energy gives you a good quantum number. If it is a bound state, then n, the principal quantum number, becomes a good quantum number. If you can measure the orbital angular momentum, it becomes a good quantum number, but it is not, because L couples to the spin, and the good quantum number is neither L nor S, but J, which is, yeah. So, you get appropriate quantum numbers. Kappa is the relativistic quantum number you get from the solution to the Dirac equation. So, this is not coming from Schrodinger equation. So, the quantum numbers that you see in this equation are not Schrodinger quantum numbers, they come from the Dirac equation, because we begin from the very start with a fully relativistic quantum mechanical theory. Schrodinger equation is not invariant under Lorentz transformations. Schrodinger equation has got V of r, for example, which is the space part, but space interval is not Lorentz invariant. What is invariant is the interval in the space time continuum. So, Schrodinger equation is not appropriate to represent relativistic phenomena. One can use it artificially by introducing relativistic terms in a perturbative manner, and it works as far as it works, but it cannot work fully, and it does not work fully. So, the more appropriate way is to find what quantum equation will be invariant under the Lorentz transformations, and that was discovered by Dirac by figuring out that he must represent certain operators, take into account the matrix structure of those operators, and what we get out of it is what we call as the Dirac equation. So, n kappa are the quantum numbers we get from the Dirac theory, but you will find that also in my book.